shall look at few problems on real gases. We start with a simple one. Determine the compressibility factor for nitrogen at 10 megapascal and minus 80 degrees centigrade and at 0.5 megapascal and 35 degrees centigrade. So here we have to find out the value of compressibility factor, that is Z. Okay, for nitrogen gas, they are given two conditions. One is pressure is 10 megapascal and minus 80 degrees centigrade is the temperature. And second condition is pressure is 0.5 megapascal and the temperature is 35 degrees centigrade. So now you have to go to the table for this critical properties, because to find out the compressibility factor you have to find out the reduced pressure, reduced temperature. Okay, so to find out reduced pressure and reduced temperature we should know the critical properties, and thus we will go to the table for nitrogen. Okay, now you can see now this is a table for critical constants. Now you can see the table for nitrogen, that is third row. Nitrogen critical temperature is 126.2 degrees in Kelvin you can say, and the critical pressure is 3.398 megapascal and the critical volume is 8.99. So from the table of critical constants, what we have seen for nitrogen, critical temperature in Kelvin is 126.20, critical pressure is 3.398 and the critical volume is 8.99. So these three we are going to use in this to find out the reduced properties, and from the reduced properties we are going to use the compressibility chart to find out the critical compressibility factor, that is value of Z. So Tc is equal to critical temperature 126.20 Kelvin, critical pressure is 3.398 megapascal, critical volume is 8.99 into 10 raised to 2 meter cube per kg mole, that is molar specific volume it is. Now first condition, at 10 megapascal pressure and minus 80 degrees centigrade for nitrogen. So reduced pressure PR is equal to P divided by PC. Here pressure is given as 10 megapascal and PC is also in megapascal. Okay, so there is no need to change any units. So both are in megapascal. So 10 divided by 3.398, we get the reduced pressure as 2.493. This is a reduced pressure. Now reduced temperature. So reduced temperature is equal to T by Tc. Okay, the temperature given is minus 80 degrees centigrade, whereas the critical temperature is given in Kelvin. So both we are converting in Kelvin. So minus 80 plus 273 divided by critical temperature 126.20. Sorry, it is not 20. The reduced temperature is 1.528. Okay, so reduced temperature is 1.528 and reduced pressure is 2. So now you can see here using this table. This is very important. We have to understand how to use this I think I will show you. Now reduced pressure 2.5. This is the 2.5 line. So I will draw this line like this. Okay, and the reduced temperature is 1.5. You can see the reduced temperature is 1.5 here. So this is the point. Okay, then I will take it left. So it is slightly above 0.8. You understand? So first we will take the reduced pressure 2.5. Then we will take this line. This is a reduced temperature line 1.5. Okay, wherever they intersect, this is the point where it is intersecting. Then I will go to the left and coming to the this is G, this is G or the compressibility factor, and here it is shown. So the 1, the intersection point is 2, and this is 3. This way you can find out the compressibility factor, that is the value of Z. So you can see here uh, the referring compressibility chart for PR and TR. Okay, so PR is 2.5, TR is 1.5. You got Z is equal to 0.84. Now next, for next condition is 0.5 megapascal and 35 degrees centigrade. So again 35 degrees you have to add 273 to convert it into Kelvin. So reduced pressure is 0.5 megapascal divided by 3.398 megapascal. You get is 0.147. You should always understand that units on the top and bottom should be same. You can't put one side kilopascal, one side megapascal or bar. That uniformity of units has to be maintained. Second, reduced temperature is 35 plus 273 divided by 126.20. You get as 2.44. Now you can see here, uh, uh, here the reduced pressure is 0.147. Reduced pressure is 0.147 and the reduced temperature is 2.44. Okay. Now we shall see the compressibility chart. Now you can see 0.144 reduced pressure means it is very close to this. It is very close to. So it is very close to the uh, this value near to 0, 0.14 because next is 0.5 only. So this is the line. Okay, this is the line which is nearing 0.144, that is reduced pressure. Now the reduced temperature was 2.4. So reduced pressure will be some, now it have given up to 2 only. So you take here, so the reduced temperature is this. Okay, so first I have taken reduced pressure, that is 0.144. Then I have taken the reduced temperature, that is 2.44. They both intersect at this point. So this point is nearly 1. This point is nearly 1. Okay, this is the value of Z. This is the value of Z. So now you can see in this problem what he has told. From the compressibility chart, Z is equal to 0.99. Z is equal to 0.99. So what you understand from this numerical, if the reduced pressure is very low, if the reduced pressure is very low and the reduced temperature is very high, then the gas behaves like an ideal gas because Z is almost equal to 1 here. Okay. So this is the takeaway from this numerical. Hello students, now we shall look at one more numerical on real gases. Determine the mass of nitrogen contained in a 30 meter cube vessel at 20 megapascal and 200 Kelvin by using A. the ideal gas equation of state and B. the generalized compressibility chart. So there is a vessel with a volume of 30 meter cube. In that nitrogen is stored. Nitrogen is normally stored under pressure. So this is at 20 megapascal. If you want to convert into kilopascal, you have to multiply with 1000. Okay, and the temperature is given as 200 Kelvin. So it is like sub-zero temperature. Okay. Now ideal gas law is PV is equal to MRT. Now we have to find mass. To find out mass, what I will do? M is equal to PV by RT. Okay. M is equal to PV by RT. So substituting the value, M is equal to P is 20 megapascal. So 20 into 1000, that is 20,000. And volume is 30 meter cube. Okay. P into V हो गया, divided by R is 8.3143 divided by 28. Nitrogen is N2. N2 means 14 into 2 is 28. Okay. And T is 200 Kelvin they are given. So they are given pressure, they are given volume, they are given the temperature. You know the molecular weight of nitrogen as 28. So you found out the mass as 10103 kilograms. Okay. This is using an ideal gas equation with the relation PV is equal to MRT direct. Now we have to use compressibility chart. Okay. Now for compressibility chart, what they are given? if you look at this table for critical pressure and critical temperature, now if you look at the third row, nitrogen N2, what is given here. So the critical temperature is 126 Kelvin and critical pressure is 3.398 megapascal. Okay. So, and the critical volume is also given as 8.99. That is molar specific volume. So we will use these relations. Like for nitrogen, the critical properties we have seen as 126 Kelvin is the critical temperature and 3.4 is the critical pressure. So this we will use in the for comp. Now we have seen that P is critical pressure, PC is 3.4 megapascal, TC is 126 Kelvin. So reduced pressure is actual pressure divided by critical pressure. So actual pressure is given as 20 megapascal, that is 20,000 kilopascal, divided by this critical pressure is 3.4 megapascal, that is 3,400 kilopascal. So you get reduced pressure as 5.88, and then reduced temperature is nothing but actual temperature, that is 200 Kelvin, divided by the critical temperature, that is 126 Kelvin. So you get TR is equal to 1.598. So now you got what you got. Now what we have got, reduced pressure we have got as 5.88, PR is 5.88, or you can say 6, it is very close to 6, and then TR is 1.585 or 1.5. Okay, so 1.5 TR and 6 PR, we will find out the value of Z from the chart. So now you look at this chart here. Now you look at the chart. Now this bottom is PR, reduced pressure. So reduced pressure he has given us 6. So this line is the reduced pressure 6. Okay, and TR was 1.5. TR was 1.5. So TR 1, 1.1, 1.2, 1.3, 1.5. So this line is the reduced TR of 1.5. So this is intersecting at this point. At this point, what I will do, I will take the left like this. So this will give the Z value. So what I have done first is PR, reduced pressure. This is number 1. Okay, then I found out TR lines are given like this. So this was a TR line. This is number 2. The point of intersection, I had taken it to the left and I got the value of Z. This way you find out the value of Z. So you can see from the compressibility chart, we got the value of Z as 0.902. In chart you will not get 0.902, you will get only 0.9. Okay, because they are not accurate to that 3 digits and all. Now we know that PV is equal to ZRT. So V is equal to ZRT divided by P. So Z we have found out as 0.902. R is 8.3143 divided by 28. Molecular weight of nitrogen is 28. Temperature is given as 200 Kelvin. Divided by pressure is given as 20 megapascal or 20,000 kilopascal. So V is 0.002677 meter cube per kg. Okay, and if I want to find out the mass, now for the general compressibility chart, the mass we will find out mass is equal to volume divided by specific volume. Volume is 30 meter cube, specific volume is, we have found out 0.002677. We found that the mass is 11,206 kg. Now you can see in these two solutions what we have found out. The mass of the gas in a 30 meter cube cylinder was 10,103 kgs. Okay, 10,103 kgs if you calculate using ideal gas equation. But in real gas, when you are using the compressibility chart, we have found out the critical pressure and critical temperature based on the chart, critical parameters which are given in the chart, and from that we found out the reduced properties, and using the reduced properties PR and TR we found out the value of Z, and substituting the value of Z in PV is equal to ZRT, we found out the specific volume. and from the specific volume you found out the mass. Mass is equal to total volume divided by specific volume. So you found here that the mass is not 10,103, but it is more. It is more than 1,100 kgs more. It is 11,206 kg. So this is a actual difference between ideal gas as well as real gas. So in real life, we need to consider the real gas equations, and here we are in this problem we have used the compressibility chart to find out the mass. Thank you. Hello students, now we shall see the next numerical on real gases. Calculate the pressure of 3 mole of air at 300 Kelvin with a total volume of 0.8 meter cube. Use the ideal gas law and the Vander Waals equation of state. So here we have to find out the pressure of air, 3 moles of air at a temperature of 300 Kelvin, and the volume is 0.8 meter cube by using two things. One is ideal gas equation and second is Van der Waals equation. Okay, so first we will go by the Van der Waals equation. We know that the specific molar specific volume V bar is equal to V divided by N. Capital V is volume, N is the number of moles. So volume is given as 0.8 meter cube and N is given as 3. So you get V bar is equal to 0.267 meter cube per kg mole. This is molar volume. Now we have to find out the for Van der Waals equation there are two constants A and B, and here it is air. So we will find out the Van der Waals constants A and B from the table. So this is the table for Van der Waals equation of state. In your thermodynamic data book, these are all available. These whatever constants are there for Van der Waals equation or critical temperature, pressure, and critical properties like. And third is the Beattie Bridgeman constant. These are all available in the thermodynamic data book, and this data book is allowed for your examinations. Now you take the case of air. First row itself is air. Okay. First row you can see is for air here. Here the A volume of value of A is 135.8 and value of B is 0.0365. So we will use this value as 135 and 0.0365 in the Van der Waals equation of state. So you can see here the A value is written as 135.8 and B value is written as 0.0364. Now using the Van der Waals equation for state, we know that P is equal to R bar T divided by V bar minus B minus A divided by V bar square. Substituting the values like R bar is 8.3143, that is the universal gas constant, into T is given as 300 K. So directly we are taken, it is given in Kelvin, divided by V bar. V bar we are calculated as 0.267, the molar specific volume, minus B, the constant is 0.0364. This constant is taken from the table for Van der Waals constants, minus A is 135.8 divided by V bar square is 0.0267 square. So solving this equation, we will get P is equal to 8.92 megapascals. So this is the value of the pressure if we calculate using the Van der Waals equation of state, which is for real gas. But if you are using for ideal gas equation, now we'll go for ideal gas equation. PV is equal to nRT. Okay, so P is equal to nRT divided by V. So N number of moles is given as 3 into R bar is 8.314 into T is 300 Kelvin divided by V, that is 0.8 meter cube. We found this pressure as 9.35 megapascals. So we can see that in ideal gas equation, the pressure which is showing is 9.35 megapascal, which is different from the Van der Waals equation of state, which is for real gas. We find this as 8.92. So this is how you solve the problem using Van der Waals equation as well as ideal gas law. And when we have solved the Van der Waals equation, what we have done? We have taken, first we have calculated the molar specific volume, that is V bar is equal to capital V divided by N. We found the V bar. Then we found the A and B from the Van der Waals constant tables which are directly available. Substituting the value of A, B, V bar, R, R bar and T, we get the P. So this is how we calculate the P pressure. And now for ideal gas it is straight. PV is equal to nRT, and substituting the values we found out the value of P. This is how you can solve for pressures using ideal gas equation as well as Van der Waals equation for state. Hello students, now we shall look at one more numerical, that is determine the specific volume of ammonia at 2000 kilopascal and 160 degrees centigrade. So we have to find out the specific volume of ammonia at pressure 2000 kilopascal and temperature of 160 degree centigrade. So what we will do, this temperature 160 will add 273 to it. It becomes 433 Kelvin. Okay. Now first we'll find out this. This problem we are solving using a compressibility chart. Okay. So we will find out the reduced properties, that is reduced pressure as well as reduced temperature. And to find the reduced properties, that is PR and TR, we need to know PC and TC, that is critical properties, pressure and temperature at critical point. And this PC and TC, they are given in the table. Okay, now for ammonia we will see the table. Now looking at this table where the TC and PC, that is critical temperature and critical pressure is given, you can see NH3 ammonia is given, that is 405, that is TC, and from bottom third row, okay, NH3. So TC is 405 Kelvin and PC is 11.277 megapascals. So now substituting this value, uh, because here it is given in kilopascal, so we are converting that megapascal also into kilopascal by multiplying it with 1000. So we get PR, reduced pressure PR, is equal to P by PC. P pressure is given as 2000 kilopascal, we are writing on the top numerator, divided by PC, that is 11280 kilopascal. We have converted that into kilopascal. So this you get it, critical pressure we have converted to kilopascal, and thus you get the value of reduced pressure PR is equal to 0.177. Similarly, from the table of critical properties, we have found out that ammonia NH3. We should remember the symbol of ammonia is NH3. If you confuse and you make CH3, then it is different, gone. Now for reduced temperature, TR is equal to T divided by TC. T is given as 160 degrees centigrade, that is plus 273, that is 433 Kelvin, divided by TC is 405 Kelvin given in the table. So solving this, we get TR is equal to 1.068. Now you can see PR is equal to 0.177, they are very small, 0.177 very small, and TR is also almost equal to 1. Okay, so 0.177 PR, we will see that about x-axis, and y-axis we will see that TR is 0.1. Okay, and then we will find out the value of Z. Now you can see this again general compressibility chart. So PR is 0.177, very low, that is somewhere here. We can take this line here, this line very close to the x-axis. This is a PR is equal to 1.177. TR is 1. So you can see this line is TR1 line. This line is TR1 line. So where it is intersecting, you can see it is intersecting at this point. है ना, this point is just above 0.9. Okay, so this is the TR line, this is for TR line, this is your PR line, and this whatever intersection you are getting, this is the value of Z. So we will find out, you can see one by one. Z is slightly above 0.9. Okay, so using the compressibility chart, when we have seen for PR is 0.177, TR is 1, we get the Z is equal to 0.94. Now we have to find out R. What is R for ammonia? R is nothing but R bar divided by molecular weight. Okay, ammonia is NH3. So H3 means 3. H is 1, so H3 is 3. Then N is 14. 14 plus 3 is 17. So R is equal to R bar, that is 8.3143 divided by 17, and you will get the value as 0.4882 kilojoules per kg Kelvin. So you have to calculate this R. It is directly written here, but you have to calculate this. So we know that PV is equal to ZRT. Now we have to find out V, because we have to find out specific volume, that is small v. So small v is equal to ZRT divided by P. So if we have found out values of Z is 0.94, then R is 0.4882, we have calculated, into 433 Kelvin, that is the temperature, divided by P is 2000 kilopascal. So you get the value of V is equal to 0.0993 meter cube per kg. Okay, so the specific volume of ammonia at 2000 kilopascal and 160 degrees centigrade is 0.0993 meter cube per kg. This is the problem. So by using the compressibility chart, first we have calculated the reduced properties, that is reduced pressure and reduced temperature. To calculate this, we have taken the properties at critical point, that is critical pressure as well as critical temperature. So PR is equal to P by PC, TR is equal to T by TC. So substituting TC and PC from the table which is available for critical properties, this table is available in the data book. We found PR and TR. After finding PR and TR, we have taken the compressibility chart. Then first we have taken the PR line, straight line, x-axis. Then we have seen where it intersects the TR line at 1 with TR is equal to 1. So that is 0.94. That is on y-axis, that Z. Considering this Z, we have then now calculated the R value for ammonia. R for ammonia is, for any gas for that matter, is universal gas constant, that is 8.3143 divided by the molecular weight of that gas. And molecular weight of ammonia is 17. So you get R is equal to 0.4882. So substituting these values in the equation, PV is equal to ZRT. We want to find out only V, small v, that is specific volume. We found it as 0.0993 meter cube per kg. So specific volume will always be per kg. Volume will be in meter cube only, but specific volume will be in meter cube per kg. So this was how you can solve the problem using the compressibility chart. Thank you. Hello students, now we shall see that one more problem. The specific volume of CO2 at 120 degrees centigrade is 1.2 meter cube per kg. Determine the pressure exerted by CO2 using Vander Waals equation. If CO2 is treated as an ideal gas, what would be the pressure exerted? So now he is telling that CO2 gas specific volume at 120 degrees centigrade is 1.2 meter cube per kg. Okay, you have to find out the pressure of CO2 if it is treated as ideal gas 1, or by using the, if it is treated as a real gas, then by using the Vander Waals equation. So well, we'll find out the value using the Vander Waals equation. Okay, for that what we will do, molar specific volume of CO2, V bar is equal to 1.22 into 44. Okay, 44 is molecular weight of CO2. C is 12, O2 is 32, 12 plus 32 is 44. And here V bar is equal to capital V, that is volume, into molecular weight. Volume is given as 1.2 meter cube. Okay. So we have found out that it is molar specific volume is 52.8 meter cube per kg mole. Now we have to for this CO2 we will for van der Waals equation there are two constants A and B, and we will find out the values of A and B from the table for van der Waals equation. Okay, the CO2 gas, it is directly given. So this is the constants for van der Waals equation A and B, small a and B. So you can see CO2 gas from bottom the fourth row. From bottom, the small a is equal to 365. Okay, 365 days in a year. So 365 you can remember easily. And B is 0.0428. B is 0.0. So please here A is given as 365 kilonewton per meter square, meter raised to 4 kg mole square, and B is 0.0428 meter cube per kg mole. R bar, universal gas constant, is 8.3143 kg kilojoules per kg mole Kelvin. So van der Waals equation is P plus A by V bar square in bracket, in the next bracket, V bar minus B bracket closed is equal to R bar into T. So now we have to substitute the values. R bar is now we have to find out P. So we will rewrite this equation. P is equal to RT. Because this V bar minus P is multiplied here in the left side, it will become division here. RT divided by V bar minus B. Okay. And then this P plus A by V square was there. So P remains there. Okay. So when I take this A by V square, it is addition here. So when it is taken to the right hand side, it will become negative. Minus A bar, A divided by V bar square. So substituting the values of R bar, T, V bar, A and B, we will get C. 8.3143 into 393. Temperature is given as 127 degrees centigrade, that is plus 273, it is 393 Kelvin. Divided by V bar is 52.8, we have calculated in the beginning only, minus B 0.0428. Then this entire thing minus A is 365.6 divided by V bar is 52.8 square. So solving this, we get this as 61.8 kilopascal. So the specific volume of CO2 at 120 degrees centigrade, which is 1.2 meter cube per kg. The pressure we found using van der Waals equation as 61.8 kilopascal. Now if you want to find out straight away from ideal gas equation, PV is equal to RT. Okay. Now if I want to use directly, I am using the molar specific volume. So P is equal to R bar T divided by V bar. R bar is 8.3143 into T, temperature is 393 Kelvin, divided by V bar is 52.8. So you are getting again same as 61.8 kilopascal. So this is how, see in this ideal gas equation he has used that molar specific volume. It is not necessary you have to calculate using this only. You can calculate using normal procedure also. PV is equal to RT. Okay. So then what you will do, R is equal to R bar by M molecular weight, that you will find out. Okay. And then temperature in Kelvin and the specific volume already is given. Using this you can calculate, because it was V bar was given calculated here, he has taken V bar, otherwise you can calculate with normal specific volume also. That is also you will get the same answer. Okay. Thank you. Now we shall see a problem using Beattie Bridgeman equation. Okay. As well as van der Waals equation. So find the pressure exerted by methane. Methane is CH4. So this you should understand. Methane is CH4. In a container of capacity 2 meter cube, when it contains 3 kg of methane at 300 Kelvin. Using van der Waals equation, second ideal gas equation, third is Beattie Bridgeman equation. So molecular weight of methane is CH4, C is 12, H4 means 4, 12 plus 4 is 16. So molar specific volume is equal to V into M divided by M. So please understand these relationships properly. V is equal to 2 meter cube here given, molecular weight is 16 divided by mass is 3. So you get V bar is equal to 10.67 meter cube per kg mole. So the units are meter cube per kg mole. So volume is meter cube, mass is in kg. Now what is the gas characteristic gas constant for methane? R is equal to R bar bar M. R bar is nothing but 8.3143 divided by 16 molecular weight. So you get R as characteristic gas constant as 0.5196 kilojoules per kg Kelvin. Now we'll start with Vander Waals equation. Vander Waals equation P is equal to R bar T divided by V bar minus B minus A bar V bar square. Now substituting the values, R bar is 8.3143, temperature is given 300 Kelvin, divided by V bar we have calculated as 10.67 minus B. Now this constant B, A and B you will get from the table. I think now you are understood how to see the Vander Waals constant table. You will get the direct value of A and B. So here the value of B is 0.0427. We have seen in the earlier problem also. Minus A is 228.6 divided by V bar, that is 10.67 what you have calculated squared. Solving this, you get the pressure as 232 kilopascal. And this constants A and B are for methane, which you have taken from table 9.1. And this table, as I repeatedly told, it is available in the thermodynamic data book. Now, second, using ideal gas equation, PV is equal to MRT. Now substituting the value, mass is 3 kgs, R is 0.5196. This is a characteristic gas constant for methane. Okay, into temperature is 300 Kelvin, divided by volume is 2 meter cube. You get as 233.82 kilopascal. So there is a variation. You can see ideal gas is 233.8 means 234, but whereas Vander Waals equation is 232. Okay, now we will see the Beattie Bridgeman equation. So Beattie Bridgeman equation, you have to remember this formula. I think this formula is maybe there in the data book. Otherwise, you have to remember this relationship. Vander Waals equation is there in the data book. In the where the constants are written, there only it is the equation relationship also is written. So Beattie Bridgeman equation P is equal to R bar T 1 minus E divided by V bar square into V bar plus B bracket closed minus A bar V bar square. In Beattie Bridgeman equation, very important thing is you have to calculate A, B and E using the constants small b and small c from the Beattie Bridgeman constants. Okay, this table is given. For example, now we are seeing for methane. This problem is for methane. Okay, now you can see A is written as 0.018, B is written as 0.015, and C is 12.82 into 10 raised to minus 4. We will see this relationship from the table. So you can see these are the constants for Beattie Bridgeman equation of state. Okay, now we are discussing about methane, that is CH4. Last in the table, last gas is CH4, that is methane. So small a is 0.018, you can see. Small b is 0.015. Okay, and then C also is given here, and A naught is given 230.80 and B naught is given as 0.0590. So these last row, that is for methane CH4, these constants A naught, A, B naught, B and C, this relation you will use these form values. Now first we will calculate A naught. A naught is known, A small a is also known, and V bar we have calculated. So we will calculate A now. A is equal to A naught in bracket 1 minus A bar V bar. A divided by V bar. So 230.8 in bracket 1 minus 0.01850, that is the value of A naught, sorry, A small a from the table, divided by V bar, that is 10.67. Solving that, you get A is equal to 230.399. Coming to B, B is equal to B naught in bracket 1 minus B bar V bar. So small b value is given as 0.0158 and B naught is 0.0590. Substituting these values, we get 0.0590 in bracket 1 minus 0.01580 divided by 10.67, that is V bar. You will get B is equal to 0.0591. Similarly, E is equal to C bar V bar C divided by V bar into T cube. So C value is 12.82 into 10 raised to minus 4, that is given in the table. V bar is 10.67, what you have calculated, and temperature is 300 cube. Solving that, we are getting the value as 1.335 into 10 raised to minus 9. Now we know the value of A, capital B and small e. Substituting these values in equation of Beattie-Bridgeman equation, P is equal to R bar T 1 minus E divided by V bar square into bracket V bar plus B minus A divided by V bar square. So substituting these values, R bar is 8.3143 into T is 300 Kelvin in bracket 1 minus E, 1 minus 1.335 into 10 raised to minus 9 bracket closed, multiplied by V. V bar is 10.67 plus B is 0.0591, what we have calculated. In this relationship, only the calculated values will come, divided by V bar square, that is 10.67 square, minus A divided by V bar square. A is 230, what we have calculated, by V bar is 10.67. So you get the value as 233.04 kilopascal. Okay, so this way you can use Beattie-Bridgeman equation. So for using the Beattie-Bridgeman equation, what we have done, we have taken the table of constants for Beattie-Bridgeman equation. We have taken the value of small a, small b and small c from the Beattie-Bridgeman equation, plus A naught, capital A naught and capital B naught. So when we got these 5 constants, for Vander Waals instead, there are only 2 constants, small a and small b. But for Beattie-Bridgeman, there are 5 constants. So we will write down these 5 constants. Then we will calculate the A, capital B and small e. Once we calculate that capital A, capital B and small e, we will substitute this in the Beattie-Bridgeman equation. That is R bar T 1 minus E into V bar plus B divided by V bar square minus A divided by V bar square. So substituting this value, we will find the value of P. This is how in this problem we have used ideal gas equation, Van der Waals equation as well as Beattie-Bridgeman equation. Thank you. Please practice them so that you become more confident.